What about velocity reduction? First of all, think about it. Aren't most of your stormwater outlets designed for less than 10 feet per second? 10 feet per second is easily managed by known soft armor protection. It just won't handle the scour force accelerating immediately out of a pipe. ScourStop far exceeds this critical force. Additionally, the ScourStop engineered design takes into account traditional apron calculations and resultant forces, providing established means for determining the appropriate downstream soil protection. This design system is solid engineering, no razzmatazz. Independent research in 2005 at Colorado State University in Fort Collins, Colorado, confirmed a 50% reduction in velocity at the standard design velocity of 8 feet per second within a standard apron width and length, and that data correlates with our design software. Still, the question lingers. Explain the energy dissipation. In very simple terms, and just for quick reference, we will go through a general discussion about area expansion. Designers use the formula Q, flow, equals V, velocity, times A, area. Per the mathematical equation, velocity is significantly reduced by expanding the area. In this example, 12 cubic feet per second of water is flowing out of the pipe with an expansion area of 2 square feet at 6 feet per second. But downstream of the scour area, the same 12 cubic feet per second is moving at only 2 feet per second because the area has expanded to 6 square feet. The forces are clearly much lower downstream as the water is shallower and slower, both factors critical in shear force computation. Federal highway specifications recognize both velocity and shear for design options, but indicate shear may be a stronger model. In that regard, using rock is actually counterproductive because roughness causes a significant increase in shear as the water height rises over the rocks. If the expansion process is not utilized in the rock scenario, the high shear forces continue downstream and require heavy armor because the volume has not changed. Why do you think there are so many rock riprap failures? What about the hydraulic jump? Where does it occur, and how do we protect from it? Again, 90% of designs do not have an erosive hydraulic jump to deal with. But for those that do have higher velocities, we know from the research and field experience that the design specification is appropriate soil protection. The scour area is computed from known scour size formulas. Long-proven scientific channel protection software is utilized to indicate what soil protection is needed downstream. With ScourStop, you get mechanical protection from the high-energy forces at the scour area and soil protection with the soil cover BMP under the ScourStop. The stormwater spreads out quickly in a uniform laminar flow in most instances. The hydraulic jump occurs downstream where the water is expanded into a much shallower and thus significantly less erosive force. Other applications for ScourStop employ similar engineered calculations, independent research, and over 5 years of field experience to confidently provide you with specifications that will provide permanent, effective installations.